So good afternoon, everybody. Today I would like to tell you about two recent projects that really have been a lot of fun for me to work on. Ayelet mentioned I had fun at Pixar. It's, I try to have fun whenever I can within the confines of the academic profession. This talk is titled A Blast from the Past because what it's concerned with is how to breathe new digital life, if you will, into some older classic art and media. So in the first part of the talk will be in two parts. In the first part of the talk, I will address this issue of how to take very low resolution pixel art graphics, an example of which you see here, and convert them to a more modern resolution independent vectorized representation. And by vectorized, for those of you who are not familiar with the term, I mean a representation which does not use pixels on a discrete grid, but rather uses continuous outlines to represent shapes and images. In a similar spirit, in the second part of the talk, I will discuss how to convert classic comic art and other types of illustrations from their original printed medium into a digital representation, which is again, well, this one is semi-vectorized and semi-raster. Okay, so without further ado, let me just dive into the first part of the talk, which is concerned about vectorization of pixel art. And this is joint work with a colleague from Microsoft Research, Johannes Kopf, and it was presented at SIGGRAPH 2011 in Vancouver. So pixel art is this form of digital art where, which only has a small number of pixels, and because of that, essentially it's created by the artist literally pixel by pixel, until it comes to create the final desired shape. And this kind of art emerged in the field of video games, where essentially all the video games up to the beginning of the 90s used pixel art. And remember that then the display resolutions were very low, like VGA was wow, and the number of colors was small. And that was the driving force behind the emergence of this type of art. And also we're familiar with pixel art from earlier versions of graphic operating systems. For example, these are some icons from Windows 3.1, which, also you can see the individual pixels, and those are also examples of pixel art. So as I've mentioned, because of the hardware constraints of the intended platforms, which are like Atari computers and other gaming platforms at the time, artists had to deal with very small number of pixels and had to restrict themselves to using a very small color palette, okay? Despite those limitations, and maybe because actually some friends of mine who know more about art than I, they claim that the more limitations you put on an artist, the better art you get. So, for example, this is a very famous pixel art piece from this game, which is called Space Invaders. And I think it's quite amazing how much evil and malice you can put into an image which has 11 by 9 pixels, and it's a binary image, okay? So unsurprisingly, because of the popularity of video games, I guess, many of these pixel art pieces have become like cultural icons. And you can see them affecting our daily life, fashion, and art. And many people today still play those games, but of course they use emulators, okay? Because the original platforms are not typically, do not exist anymore. But the newer gaming platforms, they have emulators which are capable of running these old Atari and Nintendo games. But there is a problem. Originally, people were using really low resolution, much smaller screens to play those games on. And today we have these large digital screens which have many colors and they're very large. But so it does not make sense really to play this game. Okay, just a second. It doesn't really make sense to play a game on a monitor like this, but like in a window that would be about 1 centimeter square. And if you just simply upsample those images in the most straightforward fashion, you get these big squares which represent the original pixels in the image, and each square has its own color. And visually, it looks quite different from the original intent of the artist. I mean, this artwork was never intended to be seen like this. So there are a variety of ways to go about it, which I will briefly describe. But first, our goal in this work was to try to see if we can come up with a method that would upsample or upscale those images in a way that's more suitable for today's hardware and would not be dependent on the actual resolution of the device. And this is a preview of the results that we're getting from those inputs. So this is an extremely unscientific term, but I think this is really cool and this is really cute. Okay, and I mean I can put my academic reputation behind the statement. Okay, now I will explain you how we produce these kinds of results. So first of all, there are of course digital image. There are many filters that are used to upsample or enlarge digital images. Perhaps the most popular linear filter is the bicubic filter. For example, in Photoshop, that's the default filter. But of course, those filters assume certain characteristics. They assume they operate on natural images, and when you upsample natural images, essentially you just apply a low-pass filter and resample between on a new denser pixel grid, and that results in an overall perception of blur when things are upscaled by a significant factor. Okay. So that's not the way to go. Another way we've considered was to apply one of the existing vectorization algorithms. And again, vectorization is a process where you take a raster grid of pixels and you convert them to a continuous representation that consists of outlines that bound colored regions. And so this is, for example, what a state-of-the-art commercial product is producing from that same input. It's Live Trace. It's a feature in Adobe Illustrator. I think it's a very interesting piece, but it's very different from the original. I mean, I think it's more. It reminds me of like something that maybe resembles Juan Miro actually more than Dali to me. But okay. Actually, the best way of that I know of upsampling these pixel art sprites, we call them in games, is to use some specialized algorithms which the emulators that I've mentioned before actually use. And they have these lookup tables where they consider small 4x4 or 2x2 or 3x3 pixel squares, and they have lookup tables which tell them how to increase the number of pixels in each such small region. And it works better, I think, than the previous examples that I've showed you, but still you can see the artifacts of the original pixel grid, and there are some staircasing artifacts which are really a result of the original low resolution. And also these methods are limited to upsampling ratios of by a factor of 2 or 3 or 4, and that's it. Okay, once you've done that, you cannot keep increasing the resolution anymore for reasons that I probably don't have time to go into. Okay, so why is this a challenging task to try to take something like this and to convert it into a resolution independent continuous form? Well, first of all, as I've mentioned, these artworks are created pixel by pixel, so every pixel makes a big difference. Every pixel is there for a reason. For example, it could be the eye of the creature, as in this case, and we don't want any method that converts the original art into something new to lose such pixels. Okay. Another thing is that these pieces always use, or not always, but often they use thin pixel-wide lines, and these lines, they have 8 connectivity, meaning the pixels only touch in the corner. And when it's small, it seems like a continuous line, but when you zoom in, like here, the fact that pixels only touch at a corner, they cause the perception of a visually discontinuous feature as opposed to a visually continuous one. A related issue is this issue of ambiguity. When we have a configuration, a local configuration like this, how do we know which of these two colors, the black or the white, is the foreground and which is the background? Okay, so if we wanted to keep things connected to each other, do we retain this connection or this connection? Okay, in this case, it's the black one, but it's not always the case. Another challenge is distinguishing between intentional wiggling of the artwork and wiggling that's caused by the digitization of the boundary. For example, here, the mouth of this is a ghost, by the way. The mouth of this ghost is supposed to be wiggly, displaying some kind of frightening or unhappy expression, whereas the other green ellipse circles a region that is supposedly just a smooth outline of the shape. Okay, so all these are things we have to take into account, and normal image processing algorithms don't operate at a level that is that detailed. They detect edges by using filters with large support. They use segmentation algorithms that assume that you have a lot of pixels to work on, and so that's why they're not able often to produce good results on such images. So what's our idea? Here's our idea in a nutshell. Again, we observe that it is the case when let's consider this this piece here, and let's think that the pixels are just square tiles, and we have the tiling of the plane with these square tiles. Okay, so whenever we have two tiles of like colors that share an edge, then there's no problem to magnify that. They remain visually connected. But it is when the two tiles share only a corner, then when we magnify things, then visually things become disconnected. So our idea, really in a nutshell, was let's try to reshape this tiling of the plane into a tiling where cells that should remain connected as intended in the original artwork would actually share an edge. So we switch from one planar graph, which is this, to this other planar graph, which the heart of the algorithm is how to go from one to the other, okay, which I explain later. Now, once we've done that, we've solved most of the problem. Of course, we still have to trace the high contrast boundary, fit curves, and smooth those curves, and then this is the final result that we get for this ghost character. Okay, so now in a little bit more detail. So this is the input again. So we start by creating a graph where each pixel is a node in the graph, and it's connected to all of its 8 neighbors initially. Okay, but first we remove all the edges in this graph which connect between pixels of very different colors. Okay, so this gives us this graph. You see some edges here, like these edges here, they're removed. Okay, now we also note that when we have these, now we have to worry about those crossings, because our goal is to arrive at a planar graph for which we can then switch to its dual and get the tiling that we want. So let's note that we have to resolve each of those crossings that you see here, edge crossings. We have to resolve them in order to make the graph planar. So the ones that are shown here in blue color are the ones that connect 4 pixels of similar colors. So we just can remove both edges. We don't have to retain any one of the 2 edges that cross each other. So we get rid of them. And then we just are left with just the red crossings. And here we really have to decide for each such crossing, each of the 2 pixels should remain connected in the final result. Okay? So in order to do this perfectly, we really have to be able to reverse engineer the artist's thinking, which is obviously not something that we can hope to accomplish because you know, human vision and perception is still, there are a lot of mysteries there. But there are some known principles and some heuristics, and we've embraced some of them in order to get something that works on most cases that we're experimenting with. So one such heuristic is that we choose to keep the connections which form a part of a long chain, okay? And that kind of, each heuristic actually gives us some vote in favor of keeping this connection or the other, and the connection that in the end of the process has the most votes is the one that we choose. So the curve heuristic in this case would vote for the edges that are shown in yellow here, okay? A second heuristic is, has to do with this ambiguity. When examining a small environment of 2 by 2 pixels, we don't know which pixels to connect, but perceptual studies show that if you examine as larger windows, then the color which has the smaller presence, the more sparse among the two, is the one that people usually perceive as foreground, okay? So in this case, we consider this window, there are more gray pixels than blue ones. We choose to retain the connection here between the 2 blue pixels and not the other way around, okay? So this is another heuristic. And another heuristic is the island heuristic, which means every pixel, again, is there for a reason. So if we're if we have 1 pixel that's, if we remove this connection, would become an isolated island, we're not going to remove this connection, okay? So we try to choose the connections that avoid creating isolated islands, right? So these heuristics combined, we've tried our method on many pixel art examples, and I mean, it's not completely 100% foolproof, but it works very well in the vast majority of the cases. So after applying these further crossing resolutions, we arrive at this planar graph, and then we compute simply a generalized Voronoi diagram of this graph, which takes into account both the nodes and the edges that connect pixels, because essentially what this graph is, it has edges that connect pixels which should remain connected in the final result, okay? So after we switch to the dual of this graph, by computing the generalized Voronoi diagram, we get this, this styling that I've already shown you before. And now we can identify edges that separate regions that differ a lot in color from each other. That gives us a somewhat polygonal shape of the, and we would like to get a smoother shape. So we replace those straight line edges by quadratic B-splines for those just low degree polynomials, for those who are not familiar with the term B-spline. Still here you can see some residuals of the original staircasing appearance of the pixel grid, and so we apply a further process which involves some numerical optimizations to optimize some smoothness properties of these curves, and then we can get something like this. Well, this is a little too much. This shape has too much smoothing. For example, all the wiggles that we had in the mouth have disappeared, okay? This goes back to this dilemma of when is a wiggle a bug or when is it a feature, right? So again, it's impossible to solve this problem in a provably correct manner, but we've observed that essentially when a feature is supposed to represent a corner, something that's not supposed to become smooth, it falls into one of a small number of patterns. I think there are actually a few more patterns than what I'm showing here, but still it's a small number that could be enumerated quite easily, because it so happens that this graph, all its vertices are actually not on, do not fall on arbitrary locations on the plane. They all fall on either integer pixels or quarter pixels. The quantization is up to 1/4 of a pixel. So there is a small number of configurations. We identify corners. We force the optimization not to smooth over those corners. And then we get this result, which is smooth except where our detector has indicated corners. And the final step that we have to do is to try to smooth the colors in these regions where we have similar colors but not identical, we assume the artist meant that there would be some smooth gradients in color there. So we just do some kind of standard interpolation scheme, like the bicubic interpolation, in order to make that interior smooth. And this is our final result. So once again, this is the input, and this is the output. Okay. So let's see some more results. So again, this is one of our favorite is these space invaders. They managed to still convey their original evilness. And actually, this morning it occurred to me that there's some similarity between a famous Star Wars character and one of these guys. Although maybe, I'm not sure in terms of time which predated the other. I mean, what was the movie, 79? I don't remember. Anyway, I have to check that. It may be the other way around. The ancestry here may be reversed. Okay. Here's another example. Another character from another game. And again, every time we make a comparison here, I show one of the existing upsampling technique that one could have used. And you can see how we managed to trace in a, I think, a convincing way some smooth outlines of the character. And once the character has that form, basically you can magnify it or display it on any device that you'd like. Here's another comparison. This one again is with this product, vectorization product, Adobe Live Trace. So again, I think the results that we're getting with our vectorization approach, they're closer to the original artwork. And some icons here. This is a keyboard icon from the Windows set of icons. And again, I think our vectorization gives, on the one hand, it really gives a continuous, smooth representation. On the other hand, it does not introduce extraneous features or loose features that were present in the original artwork. Here's another example with a different vectorization technique, also commercial product. Okay, so actually, if you go to the project website, we have comparisons of over many pixel art pieces with about 14 different alternatives of upsampling, upscaling, vectorization algorithms. And so you can see that it's not only working on the 5 or so images that I've shown you here, it actually really works quite well. So one question, we've always been playing with just the static images. What would it look like when we actually apply it onto the dynamic game frames? So we have the emulators. So here's some screenshots from Super Mario. And this is his turtle Yoshi. And okay, so this is just what you get if you just upscale naively with what we call nearest neighbor upsampling. And this is our result. Okay, so you can get the impression that we don't suffer from any temporal artifacts, even though we have processed every frame individually and we have not considered explicitly the connection between the frames. Every frame is just, we apply the algorithm to the entire frame. So our implementation is not real time yet. So it was not really recorded in real time, but I mean, we play it at the same rate to give you an idea of what it would look like. And yeah, this is what one of these specialized upscaling algorithms would do. So it's actually quite good, but still you can see certain things which become smoother with our form of upscaling the artwork. Okay, it doesn't always succeed. This is from a game I spent a lot of my PhD years playing. So there's this part when you're supposed to write a thesis and you really don't feel like it. So These are later games, okay? We're talking here 94, well, maybe it appeared earlier, but where artists were already using high resolution artwork and then downscaling it to get the pixel art, as opposed to creating the pixel art pixel by pixel. And they use more colors as well. And because of that, the results are less, I think, convincing. But yeah, it's okay, but maybe not as I like this one less than the previous ones. Yeah, this is another example of something that we cannot handle. When richer color palettes appeared, people started using a process called color dithering in order to enrich them even more. And so for our algorithm, all these checkerboard patterns consist of 2 different colors, and it cannot tell that really those are 2 different colors that are designed to just give an impression of a single color. Okay? And sometimes things are smoothed over maybe too much. For example, in the figure 8, maybe you would expect to see some I don't know what to call them, but around the waist of the figure you would expect to see some narrowing. Okay, so this is the end of part 1 of the talk, and let's move to part 2. So part 2 deals with again, it's a matter of taking something old and reviving it with a new digital life. And in this case, our attention was on how to digitally reconstruct printed classical comic art or other color illustrations. And that is a more recent work. It was presented, it's also a joint work with the same Johannes from Microsoft Research. And we presented it at SIGGRAPH Asia in Singapore in December. Okay. So there is, I'm not sure, maybe in Israel we're a little bit behind, but in Europe, in the United States, and in Japan, there are like millions of people were really like to buy and read comic art, and comic books and graphical novels, they're very popular. It could also be evidenced by the number of movies that have been made based on such well, books and novels originally. But despite the fact that nowadays we have these devices, these mobile devices like the tablets, which are essentially, I think, perfect for reading this type of a medium, their presence on these tablets, the presence of comics on these tablets is less noticeable than we would expect. And in fact, the comics and the graphical novels is one of the it's one of the varieties of printed media which is still gaining in popularity. Okay, the analog media in all the areas that I'm familiar with, audio, video, everybody is switching to the digital representation, and comics is one field where, from some reason, they're behind in that respect. And we think that, okay, nowadays a lot of the comic art is already being created, authored on a computer, all right? And then it does appear in a digital form, and people can buy subscriptions and whatnot. But when it comes to the more classical stuff, it's very difficult to get digital versions of that. You can get some scans, but scans have this problem because they're scanned from a printed matter. When you look at them at the original size of the print, it looks fine. Then, but in what we like to do on these touch devices is to pinch and zoom in, right, into maps, into pictures, into everything, right? Because we want to see details. We want to see things larger. And if you do that to scanned art, okay, you start seeing all these dot patterns, right? Okay, so which is the it's an artifact of the way that these books are printed, okay? Because so let me say a few words about the printing process, right? So the commercial presses that are used for color printing, the vast majority of stuff that we read, like magazines, books with color illustrations, and including comics as well, they use only 4 inks to print all the colors, cyan, magenta, yellow, and black. And furthermore, these presses, they're essentially binary devices. They can either deposit some ink at a given position on the page or not deposit ink there. And because they would like to be able to create the perception of a continuum of colors, this is done by printing dots of grids of dots, and the width of the dots is supposed to be in correspondence with the desired density of the ink, cyan, magenta, or yellow. And then when they're superimposed together like this, when we look at them, essentially because they're small and our visual system makes some low-pass filtering here, we perceive this as a continuous tone. But if you take a magnifying glass, or if you scan that and magnify, as I did on the previous slide, you'll see those dots just fine, okay? So this is a process that's called, these types of grids, they're called AM screening. AM for amplitude modulation, which means that the density of the ink is represented by the size of the dots. There are other methods, but this is the most common method in the vast majority of the commercial printing machines. Okay, and so people have actually, because it's well known that this is how color printing is done, and that whenever you scan something, you have this issue. People have been developing algorithms which are called Descreening in some papers, and in some papers they're called inverse halftoning, because this process is called halftoning or screening. And we've tried, so the first thing we've tried when we wanted to try to digitize comics was to apply existing Descreening or inverse halftoning algorithms. And what we found is that although in smooth regions of the artwork they produced some kind of reasonable interpolation of the colors, they also tend to blur the crisp black line work of the illustration. And what happens that in those illustrations, in these kinds of illustrations, essentially the color is just a nice bell and whistle. I mean, the real expressiveness of the artist goes into the line work. And the line work is all done in black, and it looks really sharp here, but not after some algorithms have been applied. And people have applied algorithms in the Fourier domain and in the image space, and they go into great length into try and preserve the sharp features in the illustration, but they inevitably end up blurring some of these fine black lines. So, and the reason for that is that because they assume that all of the inks, the cyan, magenta, yellow, and also the black have gone through the screening process. They've been sampled on a raster which has a relatively low resolution. So the only thing you can do is really to interpolate and resample, okay? But the actual comic creation process is a bit different. So the first part of the comic creation process is where there's a person in the US studios, they call them pencilers, which creates a rough draft of the illustration with a pencil. That's why they call it penciler. And then there's another guy, or sometimes it's the same guy, and it also differs between the US and Europe. Okay, in Europe it's always the same guy. In the United States they have a more elaborate pipeline. It's really like a factory, and so they have the penciler, and they have the other guy who's also an artist, and he does the inking. Inking means he goes with black ink over the important lines, and then he erases the stuff that was done with a pencil and it's not important for the drawing. So this is where these two people, they create the actual artwork, and then it looks something like this. So it has no color, it doesn't have the bubbles with the lettering, but I mean all the artistry essentially, or well, a large part of the artistry is already there. Then comes the guy who does the lettering, okay? And then comes the guy who does the coloring. Now, when they actually create this artwork on a large sheet of paper, and then they photocopy it into the actual size, and the black lines are printed in paint blue on this piece of paper, and that's what the colorist uses in order to make to color the illustration. And then, so they now have two pictures. One has essentially the color, and barely any lines are visible, and the other one has the black lines at a high resolution. Okay, so then the color plate goes into this color separation process, which converts, scans the color with cyan, magenta, and yellow filters to produce masks for the different inks, and then they're going through this screening process, which creates the dots. So the cyan, magenta, and yellow inks are printed using this screening process, but the black channel, if you will, because of its importance, the visual importance, and the role it plays in the artwork, it's printed without the screening, because it's just a binary image. There are no shades. I mean, we need screening when we want to represent continuous shade on a binary device. But the black channel is already binary, so there's no issue there. So although they use CMY K printing, the K channel, the black channel, is not screened. And so when you apply the regular descreening techniques, you don't, if you apply them blindly on the illustration as you've scanned it, without first separating out the black, you blur everything, including the black. Okay, so and this is again the result that I've shown before. And so we've also experimented with a number of other approaches which are not specifically designed for getting rid of halftone screens. For example, just other combinations of filters that people on the art forums recommend, or there's a lot of work in our community on edge preserving smoothing, which tries to smooth an image only in areas where it does not have large contrasts. And you know, they work to some extent, but they always get issues on the boundaries of these black lines, because there is color and black, and they're close to each other, and sometimes it's difficult to, well, it's not sometimes, it's always difficult to tell where the black line ends and the color dots begin. Right, so what we've done then is to say, okay, we're going to separate out a mask which tells us where the black ink is, okay? And then we're just going to get this binary image. We are vectorizing it, again, fitting the discrete grid of pixels, which is a fine grid with continuous curves. And to the colored channels that remain, we can apply well, actually a number of various interpolation techniques that would work equally well. And so then we get something like this. So what the color is probably just as blurry as it was in the other techniques, but the black channel is very crisp, okay? And that's what makes the difference. So we thought it would be very simple to extract the black mask, because it's black, right? So it's not colored, it differs from the other colors. But actually we found that it was very challenging, and you know, that's why we actually ended up doing a paper about this work, because this entire process turned out to be much more involved than we first thought. So the first things we tried were to try to say, okay, if a color of a pixel is sufficiently close to black, we can apply some threshold, and we can probably get out the black parts of the illustration this way. But actually, if you look at here, where I show 4 squares which were cropped from the same page, okay? It's not from different types of, it's not from different books, it's from the same page, okay? And so there's no single threshold, and it's also very difficult to find an adaptive threshold scheme that would extract the black ink correctly. I mean, it either manages to extract too little, not everything, right, or too much, because there's no black here, It's just that the combination of the three other inks can be quite dark. I mean, you think of black as black, but when you scan it, it's not zero, right? It's we actually have various shades of gray there, and also it's not perfectly neutral. It has some color casts. Sometimes the black goes over the color inks. So the color of black is not a single color in the illustration. So if we said, okay, we can use some machine learning techniques, we can sample a black patch of a patch from a black area in the image. We can construct a color model, you know, based on some Gaussian distribution assumptions, and try to do it this way, and it only works marginally better. Okay. And then we said, okay, well, we really have to apply some regularization to this process because, you know, things are contiguous and the boundary is not arbitrary. So we know these types of problems in segmentation and other areas of computer vision. In these cases, we always apply a Markov random fields. We formulate this as a discrete optimization problem and apply a graph cuts algorithm, and get something that attempts both to recover, to identify where the black ink is, and also try to clean up all this noise that we get with the thresholding techniques. And that didn't quite work either. It was difficult to get it right. Again, it's mostly because of this great variance in the appearance of black across even a single page of a comics book. So I will just briefly explain you then what solution we did take to solve this problem. So starting from a scanned image which has the okay, when we scan an image, we get this image in the RGB color space, right? So because we know it originates from screens which were produced using cyan, magenta, and yellow colors, the first thing we do is we try to separate, we try to guess, well, not guess, but to approximate from the input what were the original cyan, magenta, and yellow intensities at each dot on the paper. Because we know that once we do this well, the dots will actually also be forming regular grids at different angles, but still regular grids. So it would help us in the next step. So after we try to recover the three different color channels, we try to recover the exact position and parameters of each of the three grids. Okay, and then we enter this optimization stage, which alternates between solving a Markov random field for estimating where the black ink lies on the page, and fitting a parametric model to each of these dots, which tells us how wide, what is the shape of each dot, okay? And the optimization assumes that if we get the dot shapes and the black mask right, then we can simulate the forward process of image formation, and then we should get this image, okay? So we have an objective function that we try to minimize. We try to minimize the difference between the image that we reconstruct from our model and the input image. And but the optimization, it optimizes two very different things, and so we alternate between the two. And once we have the exact black mask, we can apply the fitting of smooth curves to this image, and to apply a simple interpolation scheme to the other three channels. Okay, so all the other details are not so interesting. I mean, I just would like to mention something that in this industry of color printing, people have this standard way of predicting the color appearance of compositions of cyan, magenta, and yellow inks. There's this equation that's called the Neugebauer equation, which is a more physically realistic way of converting CMY to RGB, which is not such a simple process as we teach in our graphics courses. In our graphics courses, we just say that cyan is 1 minus the red, and magenta is 1 minus the green, etc. But in fact, in the printing industry, people use this multilinear model in order to, and this multilinear model, what it needs actually, it needs the color of the white paper, the color of the black ink, and the colors of cyan, magenta, yellow, and their combinations. So, right, this is the cyan and the magenta together, and etc. So, instead of 3 primaries, we have 8 primaries, but then these equations can be inverted. So after we invert the equation and reconstruct the grid, I'm skipping over this quickly because it's really not that interesting. We do this optimization process, which I've mentioned. And once again, we just actually explicitly model each dot as this function here. It's not a Gaussian, although it looks like one. It's actually, I have a graph of that here. Yeah, we actually modeled the dots by this piecewise polynomial profile. And so we have 6 degrees of freedom to recover for each dot. And for the black mask, at each point on the page, we have to decide whether it's covered or not covered by black ink. So we have a whole bunch, but binary variables. And so we have this energy function, which is essentially an MRF. We use a Markov random field to solve that in order to recover this mask. And once we've done that, we try to fit the profiles to each of the dots, and then we iterate in this manner a number of times. So this is the big picture here. Okay. Yeah, it's boring equations. After, as I've mentioned before, after we've managed to extract the binary image, we use standard techniques in order to fit it with continuous splines. Just, similarly to what we did in the first part of the talk. Okay, and because we have the individual cyan, magenta, and yellow grids, it's easy to produce a continuous reconstruction of the color in each of those channels, and then we use the same Neugebauer equations to recombine them together to get the RGB color. Okay, so that's the end of the technical part of that work. So let's see some results. Right, so this is again the same image. And after we apply our process, I've already shown you this result. We're able to, I think, quite accurately to trace out all these black features, including some very fine ones. What we found, though, is that oftentimes when you look at an artwork like that, when it's magnified so much, the areas of color, they become kind of boring, right? They lack texture. So, but in computer graphics, we have no problem with that. We can, if there is missing detail, we can invent some, right? So we have this process which is called non-photorealistic rendering, which means we can simulate some paper structure, paper texture, and some brush texture to say, try to give this picture a look of a hand-painted watercolor illustration, for example. So you see we've applied this filter both to the black lines and to the background, and now it's, I think it's a more appealing result to for this level of magnification to look at. Okay, here's some. So this is some screenshot from this application that Johannes put together for debugging our algorithm. So here you can see that we can zoom in and pan across the image and switch between the original scanned image and various reconstructions. So you see here, this is a reconstruction that was done with this non-photorealistic filter. Here's another example. This is without the non-photorealistic filter. These are the original dots. And this is with the non-photorealistic filter. The non-photorealistic filter allows itself to go across the lines. But I think many times people, when they draw things by hand, they do that as well. At least I did when I was 3. And we've experimented with a large number of scanned comics from France and Belgium, and also from the United States. So you can get an impression of how well it actually manages to extract this black line work accurately. Okay, so one of the things that originally got us started on this project was that we wanted to be able to animate comics illustrations. But in order to, so one type of animation which is very common is to take an image, to separate it into layers, virtually place the layers at different depth, and then create an impression of parallax, which allows you to change the your point of view. Okay, so but what the basic process requires you to do is to take an image like that, which is a flat 2D creature, and to segment it into a number of layers. Okay, and in the original representation, which was the scan that contained all these half-toning dots, it was very difficult to do. But now that we have actually a vectorized representation for the line work, and all the color is continuous, it's easy to implement a user-assisted or interactive tool, which just allows a person to just scribble a few, indicate a few areas with the mouse, and basically say, okay, this should be one layer, this should be another layer, that should be another layer, and because the boundaries of the layer between the layers, they always fall on these black lines, which we have perfectly reconstructed. Okay, having done that, we pull the layers apart, and we use standard tools. Really, it's features you can find in Photoshop today that basically take this part and fill the whole layer with the same texture. Okay, so this is how we create each layer. We make each layer extend and to fill regions which were occluded by previous layers. Once we've done that, we can do things like that. So this way we have some interesting parallax, and I think this is a much more rich way of looking at these books. You know, so long as they're already there on a digital device, right? Okay, here's another example. So this is from The Adventure of Tintin. Was done in the same way. I just haven't shown you the decomposition into layers. Once again, this method also is not foolproof. We found that the American comics, this is just the slide before last, the American comics tend to use crappier paper, and they also often tend to use darker colors. And these two things pose more of a challenge to us than the other examples that I've shown you. And sometimes some really small features which are adjoined by relatively dark areas, you know, they don't get detected as black or get erroneously detected as black. So this would be a case of partial failure where, you know, our black recovery is not as good as we would like it to be. And one other limitation I'd like to mention is that there's this whole world of Japanese comics, manga. They don't use color at all, and they use patterns, well, almost at all. And they use dot patterns in order to convey shades. So in their case, the dot pattern is a feature, not a bug. And so this is, again, something that we cannot handle. All right, so since I'm out of time and also I'm out of slides, I'll just skip the summary slide. And thank you for your attention. Oh, very long. These comics pages, okay, the pixel art is taking a few seconds per each of those little figures, because the optimization there is relatively simple, and also the images are small to begin with. Here, it's a different kind of optimization, this alternating optimization, and we use scans which we obtain at 1200 dpi. So a whole page, and we scan each page at a time. So it takes like 10 minutes to process a page. Okay, so it's not quite at the rate where you can just convert a whole book in just a matter of an hour. It would take you longer.
I guess pixel art was more interesting, and you mentioned you can sort of run real time just get the whole thing done.
Yeah, I think in the pixel art, because there's less work to be done there. I think just a faster implementation. If people, essentially all these game machines today, they have powerful GPUs in them. So I think it's just a matter of implementing some of the most critical aspects of the algorithm on the GPU, and it could run in real time. This is another issue. Yeah, this is it's a much more heavy process.
You take the pictures and then you...
No, there's no product that does that yet. I mean, Microsoft have